Yes.
Okay, excellent. All right, yeah. So I've been working for NASA since about 2008, and I have been doing this role for about a year and a half as the lead for the design of lunar surface habitat. I'm going to talk a little bit about the habitat itself, a little bit about Artemis, and then give you some nice little videos and talk through some of the challenges as well. So first things first is that there's this thing that we're trying to develop. It's called the Artemis Base Camp. And the idea behind it is that we want to have a long-term sustainable architecture on the lunar surface that we can do operations on the lunar surface with. We can do exploration, we can do science. That science could include things like geology on the surface, certainly exploring the surface, but it also could be medical and life sciences and other things. This is something that we want to be able to do so that not only are we learning for the work that we're doing there and in the operations and how to do those operations on the surface and to create a sustainable architecture in that sense, but also to help us go to the next level, which is going to Mars and other planets. We need to learn how to operate in these environments. So one of the things that's the central portion of this Artemis Base Camp is this surface habitat, the lunar surface habitat. And this surface habitat, as you can see here right now, we're looking at an idea that is a hybrid metallic inflatable habitat. So this top portion is an inflatable or soft goods type of habitat. Now you might think, when you think inflatables, you might think squishy like a balloon or something like, something like a latex balloon, but they're not like that at all. In fact, if you even put about half a PSI of pressure inside of these things, they become pretty much as hard as aluminum or as hard as rock. So the idea here is that with an inflatable habitat, you have the advantage of being able to be put into a smaller launch vehicle fairing and still have the volume or the space that you need to do the work that you need to do and the living that you need to have on the surface. So you're not constrained as much by that launch vehicle fairing. There's some challenges associated with doing that, but it's some things that we're also doing a lot of analysis and study on. And then we have this particular design right now is looking at a 3-story vehicle. On that first floor, you would have your airlock where you would do operations, where you would go in and out of the vehicle itself. You would bring in new supplies as you need them. And then on the upper levels, you would have things like living space and places to eat, galleys, things like that. You would also have a restroom, of course, on this habitat. And then you would also have science equipment, things that you would need to do in terms of that science. Then the whole idea behind it is to, like I said before, enable a sustained lunar presence. It gives us an opportunity to extend the duration of crew being on the surface, extend the amount of crew that we can put on the surface. As you can see here, it's designed for about 2 to 4 crew, 30 to 60 days. And like I said before, it's going to facilitate that Mars preparation. Now, it does this in a number of ways. One, it does it from an operational level, but it also does it from a technology level. You can bring technologies to the surface habitat. You can start to test them and try them out, and then you can try to advance that technology so it's prepared for things like Mars. And then we also have this capability of doing EVA and suit maintenance. You have to have the ability to do suit maintenance, especially when you're doing a lot of long duration lunar surface exploration, because the suits are going to get shredded up, as you can imagine, by the surface material. So you're going to have to do some replacements of things like gloves, and then you might have to do larger operations or replacements or maintenance on those suits in order to keep them functioning for that entire time. Then we also have to generate our own power and store our own energy, which I'm going to talk a little bit later about some of the challenges inherent in that, because what we're looking at right now in terms of where we're going to go for Artemis is we're talking the lunar South Pole. And the lunar South Pole offers some advantages, but there are some things that you have to still to work through as in terms of challenges. So I'll get to that in a moment. But we have to be fully self-sufficient. That's really the bottom line there. It's also a surface communication hub. It's going to offer capability for communicating with other surface assets like pressurized rovers, with suits, with crew that's on the surface, and then also direct to Earth communications. And then one of the things that's maybe not listed here is that science portion that I talk about. It is meant to be a science platform as well. All right, so we have some key design considerations when we're talking about the surface habitat. One of those is delivery mass. It costs a lot of money to send something into space. And we talk about low Earth orbit, which is where where the space travel is going right now, right? Into ISS and things like that. That's one thing, but then to get it all the way to another planetary body and its surface, that's a whole nother thing. So when we're talking low Earth orbit, we're talking a few hundred, 500 or so, a couple hundred kilometers above the surface of the Earth. Okay, so you're talking a few hundred kilometers away, right? But when you're talking about the moon, you're talking about 400,000 kilometers away. So it's a lot more distance that you have to travel. It's not so much the distance, but part of it is also getting to that surface, right? When you're leaving a gravitational body and getting out, you have to have a lot of energy and then to get to the surface. We have to consider the functional volumes. How much space does a person need to sleep, to do their own activities, to do hygiene, to clean themselves, to go to the restroom, to commune with other astronauts, to eat, those types of things, or even to work. We don't want to have to be cramped up and not be able to do the work that we have, or slow down that entire process, or make it difficult for us to get sleep and for us to really feel like we're contributing to the mission without getting stressed out. So that's one of the things that we have to consider. And then another part of it is what's this ECLSS, which is Environmental Control and Life Support System. And that's the loop closure. So environmental control and life support system helps us scrub the carbon dioxide out of the atmosphere, helps us to continue breathing good oxygen, things like that. It provides us our water and all that. But if we close the loop a little bit more, as how we term it, what happens is we're able to now pull condensate out of the air, the sweat that you might have given off, or even from urine, and then translate that back into drinkable, potable water. So being able to do something like that is a very critical component, or even to produce oxygen in situ. In situ just means on the surface where you are, right? And you could do that in a number of ways. One is you could pull water ice from the surface, and then you could try to do electrolysis and pull oxygen out of that. Or you could actually just have the water with you. So there's a lot of different ways that you can do that. What that does is it buys down on the whole architecture, as we would call it, the ability to prevent additional landings of additional supplies. And so that would bring down the total mass that you have to land, which brings down, of course, the cost. As we talked about earlier, it takes a lot of energy. So we have some challenges. Whenever you're on the lunar surface, you've got some major thermal conditions, right? Hundreds of degrees Fahrenheit. You're swinging from cold to hot, right? That sort of thing is very tough on systems. It's very tough in order to maintain the thermal conditions of those systems, and it's something that we have to be able to address in order to keep those systems fully operational for a long period of time. Another aspect of this, and I think it's pretty obvious, we've talked a little bit about this, how it shreds suits, is dust. Dust could get into our systems, and it could, if it intrudes inside the habitat itself, it can make it very difficult for those systems to operate. It's electrostatically charged dust too, so that doesn't really help things. And it actually can cause system malfunctions and failures, and we don't want those types of things. So we have to mitigate that dust and do that in a way that optimizes the amount of crew time that we have to actually do operations, rather than just spending your entire day cleaning off your suits before you can even enter the habitat. You want to be able to have systems and concepts that can help you to mitigate that dust. It also affects things like seals. These are vehicles that have to keep a pressure in them, and you want to be able to have those seals actually seal consistently. Every time you close a hatch door, you want it to be able to do that. Lighting and eclipse periods. I'm going to have some little videos or little video animations to show you on what this really looks like, but it's a very critical thing, both for visibility. It's also a critical thing for systems themselves in order to both on the thermal side of it to maintain their environments, but also on the power side, because those are really inextricably linked. You have to be able to heat that system. You have to be able to keep that system going and operating through those night periods. So you're going to have some sort of energy storage or production that's not really dependent on light. And then you have radiation. Radiation affects systems. This is why we have to do radiation hardening for space operating vehicles all the time. But it also affects humans themselves, right? You have solar particle events. You have galactic cosmic radiation. All of these types of things can create cancers in long-term exposure to them. And it also can create short-term very detrimental effects neurologically and other things. So we have to find ways of mitigating radiation. Gravity. We think 1/6 G, it can't be that bad, right? It's 1/6 the gravity of Earth. Well, I mean, you know, we've got gravity, right? We're good to go. Well, not necessarily, right? We've done a lot of our learning on things like ISS. We're in a very microgravity environment. We don't have that much gravity, but sometimes engineers and others can take for granted that 1/6 of the gravity of Earth is going to be sufficient enough for humans to function and be fine over long term. We're not entirely sure. There's a lot of questions that surround that and how we're going to address that. In the past, and I think as we go into the future as well, we've had to do countermeasures. We've had to do exercise machines and other things in space that we're going to have to continue to do in a 1/6 G environment. Then there's terrain. You can imagine there's no roads, there's no roadways on the surface of the moon. Not that we couldn't build them, but that we don't have them currently. And there's a lot of different terrain issues that you have to navigate. And when you look at the moon, it's pretty pockmarked with a lot of craters and things like that. There's boulders, there's rocks, and you have to be able to navigate that. And you have to be able to land a habitat within that and actually maintain some sort of leveling capability for that hab. There's another thing it's outfitting. How am I going to put things inside of my vehicle? For metallic habitats, it's a little bit easier to just sort of put everything where you're going to have it when it's finally landed, or at least for the most part that way. And then you could just leave it. It's done. But in an inflatable habitat, you can imagine now you have to start moving systems around, and then you have to bring in any new systems that you need as the missions continue to go on year after year. And then finally, there's also logistics transfer. Logistics, we have to be able to get all the supplies that we need inside of the habitat. We have to get them off of other things. And we have to be able to do that in a safe manner for the crew because we're going to need a lot of things to bring with us. You can't just go on this trip without bringing everything with you. So just kind of to give you an idea about what these lighting challenges are, when you're looking at the South Pole, you can see these large shadows that are cast as the sun moves around the South Pole. And it's because a lot to do with the terrain, the angle at which the sun is from the surface. We can see that the sun really is hovering about 3 degrees above the horizon, and it casts extraordinarily long shadows. This can be very difficult. You have to really plan your missions. In this case, we're looking at more of the summertime, and it's starting to move into sort of the spring period here, or actually maybe it's the fall, because now we're on the South Pole. We have to kind of think of it the other way. And when you start to consider, I have to land within these portions, or I have to survive these dark periods, or I have to traverse different areas on the surface, this can be a major challenge. Even just seeing what you're doing. Imagine driving your car. I used to live in Colorado Springs. I remember the idea of trying to drive your car up a hill, and there's the sun just blaring right in your eyes, and you have no idea how in the world you're going to drive your car any further without just running into somebody. It can be a very terrifying experience. Thankfully, there's not a lot of vehicles on the moon, so maybe you don't have to worry about that, but you don't want to drive into a crater either. So there's a lot of things that you have to think about in terms of lighting. So here's just sort of another example, I think, during more of the, maybe it's starting to go from the summer into the fall, or spring rather, and then it's going to end up into the summer again. And if you were to look at it from the surface, you can see how even the Earth, right, we're tidally locked with the Earth. So what you would see is the Earth really stays in one portion of the sky really the entire time, but it's going to go below the horizon. It's going to come back up, and there's going to be times where you're going to have blackout and in the ability to communicate with Earth. And then you have the sun just kind of rolling around this, providing you a lot of darkness, a lot of shadows, and then small patches of light. We even consider them sort of like islands of light that you want to drive into and try to navigate based off of lighting conditions so that you can have solar power or things like that. And then using your batteries whenever it's absolutely necessary. But also remember, when you start going to the shadow period, the thermal conditions start to change significantly, and it could get extraordinarily cold. So then you have to have suits that are capable of withstanding that, and or even other systems that if you're going to be in that darkness period. All right. So one of the things that we're doing in order to accomplish all of these goals, especially with the design of a surface habitat, for instance, is that NASA has really been moving forward with trying to work with both commercial and international partners. It's essential that we have other groups like these on as a part of that team, because going to the moon is already not easy to do, and our international partners offering things makes it a little bit more affordable and offers us more capabilities, both enhancing and enabling. And then our commercial partners are going to be providing a lot of the vehicles and the support that we would need on the surface by providing us services. And that's what I wanted to talk about today. So if you have any questions, let's go ahead and go into Q&A.
Thank you so much, Kessler. Any questions? Yeah.
So whenever they're working on the redesign for these spaces, are there any files or documents with the existing kind of dimensions that we can look at to know how wide or how small those spaces are with the lunar habitat?
I'm not sure if I heard the whole question. Were you asking about, is there any documents to look at the size of the actual habitat itself?
Yeah.
Like dimensions and stuff?
Yeah, so if they're going to design within these spaces, within kind of the existing shell that they have, are there any files, documents, anything that say how wide, how tall certain things are, anything like that?
Yeah, I have written a paper that was given to IEEE. I can take a note and see if I can provide something like that. I think I have something that we've already done in terms of our paper that will have some of that information that you're looking for. So I'll have to go back and check for sure.
Great, thank you.
Thank you so much. Are there any other questions?
Yeah.
Yeah.
We have a stroke line, and what is the constant temperature and humidity of that facility?
I'm sorry, what's the constant temperature on the habitat itself?
Yes.
Oh, okay, yeah. So we try to keep it at a temperature that's comfortable, right? It's kind of like if you're in your own house or whatever. It's going to be a little bit dependent on the astronauts themselves and what their comfort level is. But you're probably talking between, maybe 68, 69 degrees to, 73 or 74. When the astronauts are not on board, it could range from somewhere around 50 degrees, which is I think is a little bit above dew point, up to about 80 degrees or so. So it could be a wide range when there's no crew on board, at least during periods of time when you don't have to like maintain any of those temperatures. You at least have to have some time to come back to that same little band, but it's going to be partially dependent on the crew itself.
And how about the humidity?
How about the humidity? Yeah, that's good question. It does have to be regulated, right? You don't want it to be extraordinarily dry in there. So we do have systems that pull humidity out of the air and add humidity back into the air. So we try to keep it, I don't know if it's like 20, it's probably bigger than that. It's probably about 40% humidity. I'm not exactly sure on the number, but it's supposed to be I think it's 40%, but it's supposed to be about a good, comfortable humidity level. We don't want it to be sweltering in terms of its humidity or feel muggy inside. Also, the humidity is a very crucial part in terms of preventing microbial growth on the walls of a habitat or on all other systems. You don't want it to be too humid so that it does that. But we do have a comfort level that we have to maintain for the astronauts.
I have a question.
Mhm.
How much microgravity does the astronaut feel inside the space station? Is it negligible?
I didn't really hear that question at all. Could you try
The
again?
level of gravity that an astronaut would feel inside the ISS, is it, did you have a measure? Is that what,
Is it negligible? Like,
is it negligible, the amount of gravity that an astronaut would feel inside the ISS?
Yes. Yeah. It's well. Yeah. I mean, we call it microgravity. I mean, a lot of times we talk about it as 0G because it's essentially like you really wouldn't feel gravity, right? Like it's imperceptible, right? So that's why we always call it 0G. And versus the lunar surface where you actually could stand up in microgravity situations. If you push off of a wall, you're going to go flying into the next wall, right? There's no on the surface of the moon. You could see even from older video of the Apollo missions, jumping. You could jump extraordinarily high, right? I mean, take your weight right now and cut it to 1/6 of what that weight is, and then add a suit on top of that that's maybe 150 pounds or 100 pounds or whatever, and that's what you're going to weigh. And you could certainly jump really high. And if you're inside a hab and you don't have a suit on, you could jump even higher. But at the same time, you don't get stuck in situations where if I was between two walls and I can't touch anything, then I could end up getting stuck. And some astronauts have for brief periods of time been stuck where they can't get anywhere. It's just kind of like floating in water where you can't get anywhere.
I think there was a question from an online person. Tushar?
Oh.
Are there any other questions? Yes.
What is the astronaut exercise routine like while being in space for however long they are?
The question is, what's the astronaut's exercise routine?
Yeah, right now on ISS, I believe it's something like it might be 90 minutes or 120 minutes of total exercise time. You have to do a lot of exercise at ISS in order to prevent bone loss, to keep your neurovascular system going, to keep your all of that stuff just as healthy as you can, with still having some atrophy and detrimental effects that you're going to experience. It's still right now, it's still a big question mark. How much exercise are we going to actually need to do outside of doing things like extravehicular activities, which is what EVA stands for. I never mentioned that before. But yeah, it's going to be probably on the order of an hour or so every day.
whatever inside the lunar module.
Can you?
Whatever inside the
I can't hear you.
inside the lunar module, do you have to do the exercise
Oh.
for
Inside the lunar module, do the astronauts have to do exercises and such?
Yes. Yeah. Well, you're talking about like inside of the human landing system. Yeah. It really depends on the amount of time that I think they're going to be there and what the exercise community is going to desire. But the habitat itself is meant to be designed for doing some of that. And even the pressurized rover would have to have some sort of exercise device, because when we bring on the pressurized rover in the Artemis program, I think it's the first one to come out of the two. Is the pressurized rover, then the surface habitat right now is what we're notionally thinking. The pressurized rover itself is supposed to increase the crew duration to 30 days, but it's going to be only 2 crew on the surface. And once you get to about that 30-day mark, and you're going to have to start doing that. The initial human landing system is going to be on the surface, and I'm not exactly sure if they're really going to require exercise or not, but they're only going to be there for about 6.5 days initially.
okay, I have a question. Whenever they are doing the exercise, they are sweating, right? And does their clothing create any barrier to evaporate that sweat?
It probably it does. I mean, it does in the same way that you would in on Earth, right? I mean, you would still have the same, your clothing. If you wear like dry shirts and things like that, they're going to evaporate the sweat a little bit more easily. I'm not sure exactly what the clothing is that they're wearing in order to do that. But it shouldn't be, I'm not sure how that's going to change in terms of 16G or what it is in terms of ISS. So that's a really good question. I'm not exactly sure what the answer is on that, how it changes.
So inside of the ISS, you have to work out like what you said, that 1 hour to 2 hours. So you are sweating, and what I want to understand that is that the sweating, it is not going to drop off, or it is not even evaporating because there's no air. So it is like inside. I mean, it is on your body. So what is your like cleaning procedure after the sweating, after the heavy workout, something like that?
Yeah, okay. So one is that you would let's say you do your exercise, that sweat that you get on your clothes and things like that. A lot of times they have like disposable clothes. They throw away clothes. Yeah. That's really what they do. There are systems that people are looking at in terms of how to clean clothes and things like that. There's costs to that. Like, do I need to use water? Do I need to use these other things? These are all additional weights that I need to bring with me. Is it just easier to throw them away? But when you're done exercising, they usually in a microgravity environment, like at ISS or something like that, you would use wipes and you would wipe yourself off. You wouldn't necessarily take a shower. And that's probably something that we would be looking at in terms of other missions as well. That seems to be the most efficient way. Not to say that there would never be the ability to take a shower to get all that sweat off. Am I answering your question fully?
Yeah.
Okay, yeah. So that's how you do it. And you do have air circulation. I do want to mention this too. You do have air circulation, right? You got fans going that are blowing air around you, and they're pulling off all that humidity. And then once they get into the ventilation, we have what are called like desiccant beds. You get them as little packs in like things that you might buy from Amazon or something like that, where it's just trying to absorb moisture. We can have desiccant beds where we can pull out that moisture. And in a more closed loop environmental control life support system, or ECLIS, what we have is the capability of pulling that out and then reprocessing it back into something to drink.
Okay. My next question is that inside the, I mean, when you are on the moon or something like you are walking, you have to use the suit that is supposed, it is a pressurized suit, right? I mean, it helps you to walk, or it helps you to move due to that pressure. So what about inside of the ISS? So as far as I seen that inside of the ISS, your environment is totally controlled. So they are using electrician or something like that. So that zone, I mean, do you need to have like for your better movement, like a fit, I mean, more tight clothing that will support like using some sorts of pressure, something like that?
No, they were really regular clothing. The thing is, when they have the countermeasures, they might have bands that are creating like an artificial gravity for them when you're at something like ISS, because you think if you're doing banded exercises, you're having to pull against that force of the band itself rather than just trying to lift weights. So they do those kind of things. When you're in you're right in that when you're in the spacesuit, and there's different spacesuits, right? If you have a spacesuit that has to go on the ISS, you're going to use your hands to move around. You're not going to use your legs. So it doesn't matter if you have joint movement in your legs or you can walk around. It's not even relevant. You just have to be able to use your arms. When you get on a surface, you have to be able to use your legs. So you have to have a new portion that a lower portion that has to operate in that way. And they're like having a miniature space vehicle is really what a spacesuit is. It's much like being inside this big habitat, but now I have a smaller one around me and I have to be able to walk around. Now they're lower pressure than what you would have with a habitat. And the pressure in our habitats that we're looking at right now is about 8.2 PSI. And the suits themselves, to give you an example, on Earth right now, it's about 14.7 PSI. Yeah. And we're talking about 8.2. And then the suits themselves are about 4.2, so much lower pressure.
And sometimes whenever you're doing the physical exercise, you are carrying some weight, right, inside the spacecraft. But I have a question, like if it is the zero gravity and they are still floating, so everything is like weight loss. So whenever you're trying to pull the weight, so how do you create the weight? I mean, inside there is zero gravity. So do you have any special arrangement for creating any weight? Because everything is like weightless, right?
Yeah, I mean, we use the term, so we use the term weightless, and it's a little, it can be a little bit misleading, right? Weight, if we think about it, is something has a mass, right? So it's composed of matter, right? And then what weight is times gravity, right? We think about that. And so it's a force, right? And it's pulling down on us. So if you put that same mass into space, okay, the mass still exists. So now it's all about forces. So if I want to push that thing, I have to push it with enough force to move that mass. Now, is it going to be easier to move 2,000 pounds as a human being in space? Yes, because it requires very little to nudge something and move it along when there's nothing slowing it down. But at the same time, it's not like it's not like it's weightless in the sense that it loses all of its mass, right? So when we're in space, kind of think of it this way: if you were in an elevator, and they actually do this, it's called, well, it used to be called the vomit rocket or vomit comet, something like that. It's a plane where they would do these parabolic trajectories. They'd fly really, really high, and then they would drop really, really fast. And there'd be moments of weightlessness. Now you're not going against wind, so you don't feel any wind, right? It's just the normal air circulation inside of the plane. And it's like falling inside of an elevator. And you're just kind of floating around now, falling. But that's what it is when you're going around the Earth. When you're in a microgravity situation, there are gravitational bodies pulling on you, but you're essentially falling and not hitting the Earth. That's really what you're doing. You're just constantly falling. And so when you have to push up against things, you're going to have momentum. So momentum still plays a large role, right? If you want to push something, you can't just stand in the middle of two walls or something and then push it. You actually have to put your feet on some walls or put your body against a wall to push it. Because if you try to push it, it's going to move forward. You're going to move back almost about the same amount, and you're going to get nowhere. So you're just going to be doing this and never getting anywhere. So you have to have something to push against. So you always have to have that force, right? Does that help answer your question?
Yes.
Okay, cool.
To wrap up, I would like to ask you one more question. I'm your teacher. I do apparel design. Is there anything that you would like to tell us about the challenges with the design of a clothing that they wear inside the ISS or the lunar habitats? Are there a lot of fluctuations in the environment and in the environment inside those habitats that they need to design for?
I'm not sure I caught the whole amount of that question. Could you move maybe closer to a microphone? I think I missed some of that.
Can you think of any other clothing challenges they have? Like, you mentioned dust being a problem coming in, part of the dust coming inside, or the radiation, or the fluctuations in the ambient conditions, if any, or anything that you can think of that they have challenges within the habitable environments, both in ISS and also lunar surface, that my students can use that information to design better clothing for indoors environments.
Yeah, some of the challenges are, I think, the same ones that you would deal with here on Earth, depending on what you're having to design for. For instance, in an 8.2 psi environment, you have to have a higher oxygen concentration. And that's because you have to be able to breathe that oxygen, and you have lower pressure. So you have lower molecules per cubic centimeter, if you will, or a cubic inch. You have lower molecules of oxygen, but your body still needs the same amount of oxygen it does on Earth. So you have to increase the amount of oxygen molecules themselves so that there's more of them in that space. If you think about it, you know, the molecules, if you think about gases, they're moving further apart. They're staying away from each other. They're bouncing off of each other. And the less pressure you have, the further apart they get. So now you have to put more oxygen molecules to fill the space so that you could actually breathe it in. But there's a downside to that. What you have in terms of clothing is you have to take into consideration that oxygen is highly flammable. And all the materials that you have to use inside of a habitat are highly flammable if you have higher oxygen concentrations, depending on what those concentrations are. So designing clothing that actually feels comfortable and not like a fireman's suit or something like that without, you know, the shirt and the nice comfy clothes, that could be a very big challenge. You want to have comfortable clothes, or it could create a really bad psychological situation for astronauts, right? You want them to be comfortable. You want them to allow the mobility that humans want to have, right? So you don't want really tight fitting clothes. You do want something that's going to allow you to have that mobility and allow you to have that comfort, because eventually you have to go to bed at night too. And you're going to sleep in clothes, even if they're bed clothes, like blankets and other things like that. And even though they're highly flame retardant clothing, right? They could be extraordinarily uncomfortable, like wearing canvas or something. Nobody wants to wear canvas everywhere. It's not really comfortable, right? So I think that's a big challenge that they have to deal with, especially in these lower pressure environments. It's not as much of an issue in a 14.7 PSI environment, because we're talking about, I think it's 22 or 24% oxygen. And that's a much lower percentage. But as you start to go up in, lower in the pressure regime, then you have to go up in terms of oxygen content. And now you have to design clothing that's actually going to feel good when you wear it.
Thank you very much. That was very helpful.
Sure.
Sorry.
There are more questions. Is it okay to ask this?
Yeah, sure. We can go ahead and have a few more.
Antimicrobial resistance for it, or any like radiation resistance on the ISS?
I'm sorry, say that all again.
Do you need to design for radiation resistance?
Or antimicrobial?
Antimicrobial, especially on ISS.
Yes. You have to design materials that are like they're antimicrobial, they're microbial growth resistant. You also have to have cleaning methodologies that make sure that you're cleaning things to make sure that microbes don't start to grow. You have systems that actually filter that out of the air as well, because you have to think about any chemicals that are in the air. You have to pull out toxicity in the air. When you're in a microgravity environment, they have these things called carbon dioxide pockets that you can end up having. So you have to have good airflow. Otherwise you can end up, remember we talked about you're in this environment and you've got all these gases around, but now when you're in 0G, gases don't start to settle in the way that they would on Earth, right? So when you're in something like 0G on ISS, or you're doing a transit hab to Mars or something like that, you could end up getting pockets where there's carbon dioxide, a lot of it, and you have to keep that air flowing so that you don't have that. Then if you have toxic chemicals in the air, those could be, extremely dangerous. So you want to pull those out. We have what's called trace contaminant control. It'll pull those things out. It'll kill the biological things in there with heat and things like that. Then you have cleaning processes. In terms of radiation, the thing that we like to do is shelters, and they're makeshift shelters. We do those ad hoc. We do those in the moment that you need them. And what you do is you put things in your way. So that would be like if you have systems, whatever those systems are, those are in your way. And then your food and supplies, those are the things you put them in the way. So when we have a solar particle event, it's detected, there's a warning given. They know that, okay, we're going to have to deal with this. It's probably going to be an hour, maybe 2 hours. We need to make sure that there's things in our way to prevent us from getting high doses of radiation, right? Galactic cosmic radiation is a little bit different. It operates a little bit differently. The way that when it goes through materials, a lot of times it creates even worse radiation as it goes through materials. So there's different mitigation techniques. Some of those include wearables, right? Where you would wear a vest, kind of like when you go to the dentist's office and they give you or whenever you get an x-ray and they give you the x-ray gown or whatever, and they want to cover those things up. You could do the same sort of thing in space, although lead is a lot to take into space. So there's other ways of doing this. One of those is actually water. Water is a good radiation reducer, as long as you have enough of it. So you can use water vests, you can use water curtains. There's a lot of different things as in technologies for doing that. Any other questions?
What kind of technology do you use to make your clothing radiation resistant?
To make what radiation resistant?
Radiation resistant, to make your clothing radiation resistant, so that radiation doesn't penetrate the harms to your clothing and cannot hit your body through your clothing. What kind of technology do you use?
I mean, really, it's about putting things in the way of radiation. So you have to have, the reason why lead works so well is that there's this thick barrier of highly dense material that prevents the radiation from continuing through. It's going to collide with other molecules, and then it's going to get absorbed by those molecules rather than continuing its way through and hitting you. So I'm not saying that there probably some new physics idea comes out that there may be clothing that actually can do that in a better way. Those are the passive forms of radiation protection. There is options for doing things like active forms of radiation. Our Earth protects us with a magnetosphere. It protects us with a giant magnet that's created by this dynamo that's essentially in the center of our Earth, that's made up of liquid iron that's just spinning around, creating a magnetosphere. It's bouncing off all of those very dangerous radiation particles out in space. But if you ever do go and take, let's say, a flight, an airline flight, you're going to get higher doses of radiation at 40,000 feet than you will on the surface. And you're going to get much higher doses of radiation as you get near the poles, because the poles everything has to travel into that magnetic pole. So that's where the radiation comes in. In the end, though, you could have like a magnetic dynamo type system. You could do electromagnets and things like that, except these have a tendency to be very high energy. I'm not so sure that they would be good on a human necessarily. They could be very damaging to electronics, but there are some active forms of radiation mitigation that have been proposed and thought of as well. But in terms of like the fabrics for clothing and things like that, I don't know, if there's much mitigation that comes in the way of that, because usually it's just about getting things in the way.
Thank you.
Mm-hmm.
Any other questions? Our friends online, anyone who's on Zoom, any questions? All right, I think that's it. So thank you so much, Mr. Kessler, for joining us and spending so much time on this project. So thank you so much.
Thank you. You all have a great day then.
Thank you. You too.
Bye.
I was going to say, I didn't notice that because you got here and got a giant watch on the wall. Is this your like 20 minutes between class?